Hello again. Answers to those posed molecular shapes and 3D drawings. I'm going to do this I'm going to draw them, have them drawn on the board, and we'll just briefly talk about anything important about each one, and then we'll get through it nice and quickly. First three on that list of 16 was CF4, no lone pairs, standard tetrahedral, so you've got the triangle coming out, dashed triangle going away, therefore you are asked to put in a bond angle of 109.5 degrees for a tetrahedral, 109 point smudge in the case of that, there we are. So moving on to H2S. H2S, two lone pairs, so the basics is a modified tetrahedral structure and two lone pairs, 2.5 degrees each, that's 5 degrees, that means this is going to be round about 104.5 degrees. Third one, NF3, again modified tetrahedral, only one lone pair this time, that makes that angle between any two fluorines and up through the nitrogen 107 degrees. So three modified tetrahedral structures, sorry, two modified tetrahedral structures and a standard tetrahedral. And then we'll go on to the next three after the edit. See you in a moment. So here we are with the next three. I didn't mention that the third structure before the edit was Trigonal Pyramidal. Again, Trigonal Pyramidal for the pH3, which is this one. And same thing, Trigonal Pyramidal, going to be 107 degrees, and we're being joined by my chickens in the background again, and exactly the same as the previous one on C in terms of everything other than obviously the atoms. BeH2, beryllium hydride, again an unexpected molecule in some respects. No lone pairs on the beryllium, maximum repulsion pushes them away therefore at 180 degrees, and it is linear. F2O, two lone pairs on the oxygen, going to be that 5 degree repulsion, additional extra squeeze up, so that will be 104.5 degrees. There we are. So modified tetrahedral, linear, Trigonal Pyramidal. That's kind of it. See you after the edit for the next ones. So here we go with the next two. Selenium hexafluoride, analogous to sulfur hexafluoride. Therefore we have this structure here. Everything therefore is going to be 90 degrees between it, and it's the octahedral structure. That's kind of all there is to say really. And tin 4 bromide, again surprisingly molecular, I would expect for some people, and no lone pairs on the tin, so it's similar to all the other things you find like carbon 4 bromine. 4 bromines around a carbon would be the same. So it would be tetrahedral and therefore 109.5 degrees in that standard, nothing modified tetrahedral structure. We'll come back after the edit with the next ones. See you in a moment. Start to drop some jazz hands in for no reason. So C2H2 may have needed a dot and cross diagram to elucidate the structure of ethine, as it is these days known. Acetylene is as it's known by the people who use it. And it has a triple bond between the carbons in the centre, causes all sorts of things with the molecule to be fantastic. But that means that around that carbon there are only two places you find electrons, so therefore that is 180 degrees, that is 180 degrees, and the whole thing becomes linear at each carbon. So the entire molecule is like a double linear structure, so it is linear all the way through, so that's just a complete straight line of HCCH. Sulfur dioxide, again, you may well have needed a dot and cross diagram. Again, I said not in the scope of what we were doing in this video, it's long enough before as it was. And therefore, oh, plane. How exciting. Don't hear those very often these days. Sometimes it's a Spitfire, by the way. And here, the dot and cross diagram of sulfur dioxide produces a lone pair on the sulfur along with two double bonds. There is an alternative structure with a plus charge on the sulfur and a negative on the one of the oxygens, but in the end it produces the same shape, which is that lone pair and two other bonding directions means it's basically 120. It's actually not quite 120, but for A level 120 will be good enough because you have three directions that you find electrons repelling each other in. So that is trigonal planar in the sense of that with the lone pair, but of course you don't include the lone pair. So trigonal planar is not right. It is in fact bent, but not with the 104.5 degree bent that you find in water and H2S. So, slightly odd. But we'll see you for the next ones in just a moment. Okay, so xenon difluoride. One of those compounds where fluorine bullies xenon into accepting some bonding. Two possibilities. There, you probably would have needed a dot and cross diagram. So you've got 4 electrons in the actual bonding and another 6 around there making 10. But what you've got is a modified trigonal bipyramidal in this drawing here. So you've got 3 lone pairs around the equatorial, as they are sometimes called, and then the top and the bottom is the attachment to the fluorine. Now you could then put the fluorines on the equatorial, or you could actually put a fluorine up there and one on the equatorial and have it 90 degrees apart. So if you had this here, that would be 120 degrees. There it would be 180 degrees. So if you drew that one, jolly good. If you drew that one, a little special moment. If you drew the one on that side, and some people will know what that means. So, not correct, 120, 180. 180 is further apart than 120, it's the linear. This therefore becomes modified trigonal bipyramidal into a modification that becomes linear. And that's incorrect where it would be in a bent or V-shaped formation. CHCl3, old-fashioned name chloroform, is just a standard tetrahedral drawing with one of the chlorine positions being a hydrogen, 109.5 degrees, and that's the A-level angle. I'm sure it's not quite 109.5, and then you have just basically a tetrahedral structure. So PF3Cl2, going to be trigonal bipyramidal every way you do it, because you've got 5 halogens attached to the phosphorus. It's analogous to PCl5. First one, the 3 fluorines equatorially around there, and these are then all 120 degrees apart. All of them are 120, and then you've got the 90 degree axial, vertical axis down to the 3 fluorines on the equatorials. Yeah. Then you start swapping them over. So I put one F up the top. So that then means 2 Fs are still equatorial, and then we have Cl at the bottom. So then, the other version, 2 fluorines have gone top and bottom. That means 2 Cls and 1 of the Fs is left there. Doesn't have to be those two. Could put one there, because don't forget you just rotate the molecule and it looks exactly the orientation that you have drawn. So all you are doing is doing 2 chlorines top and bottom, then only having 1 chlorine top and bottom and putting a fluorine up the top, and then put 2 fluorines up the top and put both chlorines equatorial. 3 isomers. If only life were quite so, oh, it's 33% of each one, but it's not. In reality, this is the most stable version because the fluorines are further away at 120 degrees and the chlorines are down to the 90. But that's beyond A level. But those are the 3 isomers because it said in the question sheet, can you draw 3 isomers? So therefore, there's the 3 isomers. Yeah, that's the most stable, not a massively important point. See you for the last 3 in just a moment. So, last 3. This dimethyl tellurium compound. Question is, how do you have to draw it? Well, the tellurium, it's a similar structure in terms of the 2 lone pairs to water and H2S. It's Te is in the same group. It would leave you with 2 bonding directions. Now I've done it differently to the ones I've done before. I've done it with the CH3 coming out and the CH3 in the plane, but of course then the CH3 is tetrahedral. So here I've drawn the CH3 in a tetrahedral fashion, but most people when they do this will just go CH3, just draw it as a CH3 structural, because you're focusing on the angles around the Te, and that therefore would be 2 lone pairs, 104.5 degrees. O, same thing, water, bent structure, 104.5 degrees between the 2 hydrogens through the oxygen. But really the focus is on what's going on around the copper. 6 times it's octahedral. And more relevant in year 13 because this is part of transition metal chemistry, is how things go around transition metals. And finally, arsenic tribromide, 1 lone pair, nice easy one to finish. Trigonal pyramidal, and I'm sure we're starting to remember the bond angles. 2.5 degree modifier on a standard tetrahedral, 107 degrees. Didn't say what these were, these are all 90 degrees in every conceivable thing because that's octahedral. There we are done with the answers. Thank you for watching. I'll be preparing a new revision video based upon what I've been asked to do. And, well, thanks for watching. If you know how many you got right out of, there were 16 plus 2 extra, that's 18 altogether things you had to draw, I'd love to know. Put it in the comments. See you soon. Bye bye.